All right, let's take a look at section 5.2, which is properties of rational exponents and radicals. As we're taking a look at this section, we'll split it up into 2 days. There's a lot of information here, so let's go ahead and get started. The first part right here is simplest form of a radical. So what does that mean? Well, it's when a radical can no longer be simplified. There's going to be no radicals in the denominator and no fractions under the radical. Okay, so those are all properties of a radical that is in simplest form. Our second term, we have the conjugate. In chapter 4, we began to look at the conjugate. For example, if I had like an expression of 1 plus rad 3, the conjugate of that would be 1 minus rad 3. And so what that'll allow us to do is go ahead and when we FOIL it, remember the outer and inner terms cancel out. So honestly, what you really need to multiply is the first and the last. So let's just go ahead and do the whole thing. 1 times 1 is 1. We have 1 times negative 3 is negative rad 3. The inner is going to be positive rad 3. And then the last, when we have rad 3 times rad 3, it becomes rad 9, which then becomes 3. So remember, what you really don't need to do is this middle step, because look what happens right here. It cancels out. So what you're left with right here is just 1 minus 3, which ends up equaling 4. We don't have a radical. So we need to conjugate, especially when we have a radical in the denominator. And we'll get to that later on in the lesson. We talked about like terms ever since the beginning of algebra. And so this is about like radicals. And how do I know if radicals are like? It says that they have the same index. So in order for us to add and subtract radicals together, the index must be the same. All right, so let's go ahead and take a look at a bunch of different properties here. When we take a look at all these properties, in red right there, I put bases must be the same. Okay, so that is the important thing right here. If we take a look at the first property, the property of power, product of powers. And so we've talked about that last chapter or last section a little bit. And if the bases are the same, and you can see in the example, the base here happens to both be A. Right? So if the bases are the same, then hopefully now you know that we're going to add the exponents together. The little curveball that they start throwing today is that your exponents might have fractions in it. All right, so the same rules apply of adding fractions. They must have common denominators in order for you to add things up, and you're able to get your answer here. When we multiply power of a power, okay, so when we raise a power to a power, remember right here, you multiply the two exponents together, and that definitely we talked about in 5.1. So even right here, when we have a fractional exponent raised to a power, take 5/2, and it's probably easier if you take 5/2 and write it like a normal fraction instead of one that's all sideways. And so if you take 5/2 and multiply it by 2, hey, look, the 2's cancel out and you're left with 5, which you see right there. And then make sure you simplify it all the way through. A power of a product. Well, so right here inside of our parentheses, we have a times b. I could have like 5 times x or 5x. Now, we have seen things like this when we're using Pascal's triangle. So think about the rules there. When we took Pascal's, we set apart each term, we broke it down, and then we have the first term is, descending, the second term is ascending. But I guess the main rule right here is make sure that, hey, look, this exponent m needs to go to both terms on the inside. So it goes to the a and the b. What oftentimes happens right here is this. The example, let me give you a little example right here. And oftentimes I'll see, like, let's say 5x to the second power. And the problem that I'll usually get, or the answer, is 25x. So according to this, what they're saying is that this right here is wrong, because it needs to be 5 squared times x squared. So this is going to be 25x squared, should be the simplified form. And the rule that needs to be applied when we have a power of a product. Remember, with negative exponents, we never want that. So if we need to, we'll write the inverse and bring it down. So right here, we have a to the negative m power. We bring it down to the denominator. Now, instead of the negative exponent, it becomes a positive exponent right there. Okay, and then I write the inverse and then simplify in these types of questions. Next up, we have the zero exponent property. A to the 0 power is going to be 1. Okay, I can have 1 million to the 0 power. It's still going to equal 1. So there is your 0 exponent. The only time that does not occur is if your base happens to be 0. So if the base is 0, then your answer will not be 1. You'll end up with 0. The quotient of powers. What you're going to notice here is that when we take the quotient of powers, you're going to be subtracting the exponents. All right, so instead of multiplying, or adding when it was the product of powers, you're going to subtract when it's quotient. And the power of a quotient, similar to the power of the product, look at the exponent. This exponent m needs to go to both the numerator and the denominator right there. Okay, so make sure it goes to both numerator and denominator, and then simplify. All right. Sometimes what makes things actually a little bit easier, and you could take it to both numerator and denominator, but what you may notice that, hey, this a over b, you might be able to simplify that first and then just raise it to whatever the power is. That's a little trick right there that'll work on a lot of problems. Okay, so make sure exponents go to both numerator and denominator. All right, so let's take a look at some of these properties right here of radicals. And so one thing that you might be able to do, and they're showing you right here, is that you could split apart terms on the inside and then just go ahead and rewrite it as the square root of a times the square root of b. It might make things easier. Just as much as you can split things apart, you could actually combine things together. Because look, I can multiply these two together right here. We got a cube root of 4 times a cube root of 2. Now remember, the only way I could really multiply these together is because they do have the same index. So they both have the cube root. So let's go ahead. I can multiply 4 times 2 together, and then the cube root of 8 is equal to 2. But that only applies, once again, because look, my index right here both happens to be the same. Same thing for a quotient. I could go ahead and split apart the denominator, or the numerator and denominator, as long as I keep the index with both. So take a look right here. We split things apart. We have 4th root of 162. We have the 4th root of 2. Remember, sometimes you may be able to look inside right here at the radicand and simplify that. Luckily, 162 divided by 2 is 81. And so I just need to take the 4th root of 81, and that equals 3. You can't take the 4th root of 2, okay? So that becomes a problem. We'll learn how to fix that problem later on. But for now, just think. I can possibly split apart the fractions or bring them together and then simplify it first before I take whatever the index is, whether it's square root, cube root, 4th root, etc. All right, so we've got a lot of different scenarios that we're going to be looking at here. And so let's go ahead and take a look at number 1. Look at here. We are starting off with the doozy. We've got ourselves 2 to the third times 3 to the third, raised to the negative 1/2 power. So remember, we do not want negative exponents. So what ends up happening right here is I want to go ahead and rewrite this as 1 over 2 to the third times 3 to the third. And then let's go ahead, we'll raise that now is to the positive 1/3 power. Okay, so from there we have product of powers, or a power of a product in our denominator. And so remember, the rule here is that this exponent needs to go to both terms on the inside. And then when you raise a power to a power, remember, you're supposed to multiply things together. So this now turns into, let me put the work right here. This actually, if I were to split things apart, it looks a little something like this. So when I take 3 to the 1/3 power, that ends up being 1, right? 3's cancel, so I'm left with 2 right there. And then 3 raised to the 1/3 power, that ends up actually being, once again, 1. So I got 2 times 3. 2 times 3 is 6. There's my answer, 1/6. Pretty easy right there, right? As long as you know the rules and you could apply it, then this becomes a lot simpler than you think. It's very confusing with the fractions and all that kind of stuff, but try not to let that get you down. All right, let's take a look next at number 2. I'm dividing, so maybe there's a rule that we have right here when we divide exponents, or when we're dividing. Bases are the same, so that's good. Remember, when we divide or we have the quotient of powers, we're going to subtract. For our numerator right here, we do have 10 to the first power. So what do? We have 1. And then remember, the rule is we're going to subtract, and I want to subtract the exponent, which is negative 4 over 5. So we have a little more work to do. Let's take right here, remember 1 minus negative 4/5. When you are subtracting, you are adding the opposite. So let's go ahead right here, put 1 plus 4/5. And then we have to get ourselves common denominators. So we'll go ahead and put right here, this is 1 over 1. I got to multiply top and bottom by 5 to get my common denominator, and this becomes 5 over 5. Right? So 5 plus 4 right there ends up being 9. And then 5 plus 5, well, hopefully we know that that stays to be 5 because the denominators don't change. So let's go ahead and stick our base, and there you go. 10 to the 5/9 power is your answer. Let's take a look next up at number 3. Now this one looks a little complicated. There's like exponents, and then we have another exponent on top of that. So what can we do here? Well, bases aren't the same, so that could be a problem to start off with. But remember, one of the things we could do is look at their exponents right here on the inside. They both happen to be to the 5th power. So what if I go ahead and take this, and let me rewrite this like so. Or sorry, let's change that to 5. Because they both have the same exponent, right? So what if I take the exponent out? And remember, the rule here is this. If we take the power of a quotient, the power goes to both numerator and denominator. All right, so now we have that, and let's not forget the 1/6 power. So we're actually going to take this and raise it to the 1/6. Well, there's a reason why I want to do this first, because 52 over 4, I can go ahead and simplify that. That ends up being 13. So now I have 13 to the 5th power raised to the 1/6. And so remember, when I raise a power, now let's raise a power to a power. We go ahead and multiply this. 5 times 1/6 is going to be 5 over 6. And there you go. We now simplified this. All right, let's move along. Next up, let's take a look at number 6. So it says use the properties of radicals to simplify the expression. So let's think, what are things that we could do right here in these problems? The index happens to be the same, so technically I could multiply the two together. All right. What I'm going to try to show you is using some of the tricks that we've learned throughout, um, I guess, that we learned so far in the chapter to help you solve these problems. Now, you may say, well, why do I even want to bother? Because I can just go ahead and use a calculator. Well, what if you can't use a calculator? Because there's going to be some problems where you don't, especially like on the SATs. Um, or there might be some problems that where the answer is in a radical. So you got to try to figure out and solve those problems out, like uh, how to get an answer in radical form still. So if we take a look at this, one of the things that might be a little bit easier is think I have to get the same. I guess one of the main things is being able to get the same base, and that's a key thing here. And a lot of times the numbers work out so that you can get the same base. So let's start right here with this 6 root of 25. Let me go ahead and rewrite this. I want to rewrite this as 25. And if I do rewrite it, it is to the 1/6 power. Okay, remember, we had the rule right there from 5.1. So now when I take a look at 625, that's a big number. But take a look right here. I've got 25 as a base. There's probably a way, not all the time, but it's a good place to start. But I could rewrite this as 25 to the 2nd power. 25 to the 2nd power is 625. So let's go ahead and rewrite it like so. And then let's take our index and we'll write it as to the 1/6 power. So guess what? I have the same bases. Let's simplify this right here and then follow our rule. When I raise a power to a power, that will get me 25 to the, well, this becomes 2/6, which is 1/3. And then I can multiply that by 25 to the 1/6 power. Bases are the same, so it's going to be 25. I multiply the two together, and then remember, when I multiply, I have to add the powers. So I have 1/6 plus 1/3. Get your common denominators. Let's simplify this out. I could do it right here on the side. That's why you should always have a lot of extra space when you guys are doing this. Multiply top and bottom by 2, right? And then so this will become 2/6. So if I go ahead and add things up, I now have 25 to the 3/6 power, which is 25 to the 1/2. And then lo and behold, remember this right here is the same thing as the square root of 25, which equals 5. If you know your rules, it makes it simple. I know it's going to take some practice. Okay, bottom line, you're going to probably have to go back and forth to your notes, take a look at all the different rules there, and try to recall, well, what rule can I apply in each and every situation and scenario. Let's take a look at number 7. The index is both the same in these. They're both the square root, right? So how about this? One of our rules is I can go ahead and rewrite it as one whole fraction. and I go through my little calculator, I go through my brain, I'm like, all right, maybe there's a chance. 343 divided by 7, what is that? That's going to be right there, 49. It works out nicely because like square root of 49. There you go, it's 7. All right, so now we have number 7 in the books. Pretty easy, right? Let's see what we can do with number 8. Instead of trying to split things apart, we might be able to combine things together, make things a little bit easier. Look, the index is the same on our numerator. So how about let's do 250 times 10, or sorry, 25 times 10, which is 250. And then I have right here the cube root of 2. So all of this right here, once again, it's to help you kind of know the rules, understand the rules. Because I know you might be able to say just try things with the calculator, but that doesn't really help us out in understanding the rules and being able to simplify things, especially if we have variables. Okay, because the calculator can't handle a variable. So now let's see what we could do. I could divide these because they both have the same index. And so 250 divided by 2, we got ourselves 125. So I could take the cube root of 125. It becomes a nice number. And guess what? Your answer is 5. All right. Let's go on. Now we're going to take a look at some of the more challenging problems here. Simplifying an expression, or write the expression in simplest form. Okay, so let's see what we could do here. One of the tricks is to try to figure out, well, what are the different, like, we know perfect squares, right? A lot of those we know, like 4. If I take the square root of 4 is 2, square root of 9, 3, square root of 16, 4, etc. Hopefully now you know some of the ones for, like, example, like the cube roots or the perfect cubes, like 8. If I take the cube root of 8, that's 2. The cube root of 27 is 3. And so those numbers, hopefully they begin to ring a bell the more and more you do these. So how about in number 9, we might be able to split things apart to help you simplify this. Okay, especially if there's no calculator. So right here, I could possibly split things up. Now this is where you're going to use your calculator, or maybe use your brain, because that is the ultimate calculator, right? I could split this apart between 128 times 3, because that right there ends up equaling 384. So why do I do that? Because, well, right here, I could take the 7th root of 128. How do I know that? Just more practice, okay? The 7th root of 128, now think about it, it's got to be a small number, because if you take a number like 5 and you multiply it by, multiply by itself, 5 times 5 is already 25. You multiply that again, that's 125, so it can't be 5. It's got to be a small number. So how about maybe 2? So the 7th root of 128 actually ends up being 2. What's the rest of our answer? Well, I can't take the 7th root of 3, so there you go. There is your solution. All right. Let's take a look at number 10. Okay. So now this is where things get a little funky. We have to now understand how to rationalize. And the rule that you need to know is rationalize the denominator. And you're going to hear me say that again over and over and over and over and over again. Now, the hard thing is that we have ourselves the cube root. Okay, so one of the tricks right here is this. I could always rationalize by taking whatever the denominator is. If it's 9, I could multiply top and bottom by the cube root of 9. I can do that, but you start dealing with big numbers. Okay, you start dealing with huge numbers, more chances of mistakes, especially if you're not doing this with a calculator. And I keep stressing that because normally I would say, hey, no calculator in these types of problems. So what do I do instead? Okay, well, what could I take the cube root of? I could take the cube root of 8. That's going to be 2. I could take the cube root of 27, which would be 3. So if I were to find like the, I guess, greatest common factor, or actually the lowest common multiple of this, we have, let's take this right here and multiply top and bottom by the cube root of 3. And that would be our rationalizing. Why do I do that? Because if I multiply this together, take a look. My denominator becomes the cube root of 27. My numerator becomes the cube root of 15. Okay? I now right here, I could take the cube root of 27. It becomes a nice number. The cube root of 27 right here ends up being 3. And then we have ourselves the cube root of 15 up at the top. And then there you go. This ends up working out quite nice. And I can have a radical in the numerator. I just can't have it in the denominator. Okay, so don't forget. I could have it in the numerator, just not in the denominator. And this right here is my answer in simplest form. We take a look at one last one. Let's look at number 11. So remember in chapter 4, we talked about how we could handle something like this as far as the conjugate. Okay, so we're going to do two things. We're going to rationalize the denominator and get rid of by using the conjugate. Well, what would be the conjugate of 4 minus rad 5? It's just changing the middle, the sign, and it's going to be 4 plus rad 5. So right here, let's remember the conjugate. And so we have ourselves 4 plus rad 5, both in our numerator and denominator. Okay. Remember, the beauty of this is that when you multiply by the conjugate right here, when we have radical expressions, is that the outer and inner terms cancel. So all I'm going to multiply right here is the first and the last. So the first is 4 times 4, which is 16. The last is negative rad 5 times positive rad 5, which is going to be negative 5. Because it's going to be negative rad 25, and rad 25 is 5. Our numerator right here, we're just going to distribute. So I now have 4 plus rad 5. So let's simplify things out. And I've got 4 plus rad 5 over 11. And guess what? We have now simplified our expression in simplest form. As long as I do not have radicals in my denominator, then I'm in good shape. And that's the case right here. All right, there you go, 5.2a. We'll take a look at 5.2b next.